Hello guys and welcome to another calculus video. In this video we'll be taking on this absolutely stunning integral that you can see right here. It's actually from a viewer suggestion from this user right here, and it's honestly one of the toughest integrals that I've done in a very long time. Um, at first I really thought I wasn't going to be able to solve it since I've seen similar integrals in the past and I've not been able to do them, but luckily I was able to find a solution for this. So let's go ahead and jump right into this absolutely astounding integral. So there's a few things that we're going to use here. First of all, we're going to be defining the principal branch of the natural logarithm, and that's dependent on the argument of z. So we're deciding that the argument of z is going to be between negative pi and pi, including pi but not negative pi. And this is usually the principal branch of the natural logarithm. So we'll be using this for all our calculations. Note that sine of x equals e to the ix minus e to the negative ix over 2I, which means that ln 2 sine of x equals ln e to the ix minus e to the negative ix over I. We can also write these two other identities. By factoring out e to the ix or e to the negative ix, we get these two expressions right here. Notice that one of them has ix in front and one of them has negative ix, and then they have these two natural logarithms. First of all, I want to note you guys should always be careful with complex numbers whenever you're trying to split the natural logarithms like I did here, because in this case these formulas only hold for x in between 0 and pi. They may also work between negative pi and 0, but I'm not entirely certain. They definitely don't work if x is greater than pi, so definitely be careful whenever you're splitting natural logarithms. You guys can go ahead and check for yourself that these formulas do hold in this region. So let's go ahead and start on our integral. First of all, we're going to factor using the facts that x squared plus a squared equals x plus ia times x minus ia. So we factor the bottom right here. And now we're going to rewrite x in a little bit of a weird way. We're going to write it as 1/2 x plus I ln sine 2x plus x minus ln 2 sine x. And obviously if we add these together, it just becomes 2x on the inside, and of course these are equal. So if we write it out in this format right here, we can actually cancel these two factors and we'll end up with this nice partial fractions. We could have just done partial fractions directly, but I like this method a little bit better. We now have 1/2 the integral from 0 to pi of 1 over x minus I ln 2 sine x plus 1 over x plus I ln 2 sine x. So we're going to try and remove the x in the denominator here and just have a natural logarithm. You'll see why we need to do that in a bit. So we're going to use those two formulae from earlier. So in this first term, we're going to use the one that brings out a negative ix in front, and for the second term, we're going to use the one that brings out a positive ix in front, so that the x actually cancels. So we can go ahead and do that and cancel the x, and we'll end up with this formula right here, or this integral right here. 1/2 the integral from 0 to pi of I over natural logarithm e to the 2ix minus 1 over I minus I over natural logarithm of 1 minus e to the negative 2ix over I dx. Now we're going to use a really common trope in some of these types of integrals, which is when we have the integral from 0 to 2 pi of f of e to the ix dx, we can substitute z equals e to the ix, and this becomes a contour integral around the unit circle of some function g of z. And we're going to do the exact same thing here. We're not integrating from 0 to pi, we're going from 0 to pi rather than 0 to 2 pi, but we do have a 2 right here. So we're going to go ahead and deal with these separately. The first thing we need to know is when we substitute z equals e to the 2ix, this is the path that e to the 2ix takes. So when x equals 0 plus, notice I'm writing 0 plus because actually our integral doesn't start as x equals 0, it starts at x equals b, and we're taking the limit as b goes to 0 plus. That's why I'm writing 0 plus and also pi minus. That's actually very important to the value of our integral. So we have x at 0 plus, and it's going to go all the way around this circle in the path of z equals 2 to the ix. And when x equals pi minus, it's going to be just below x equals 1 right here. It never touches x equals 1, which is very important for our purposes. We can also calculate the differential right here, dx equals dz over 2iz. So I'm calling this path right here c1. So we can go ahead and set this up, and we get the integral over c1 of I over 2 times dz over 2I natural log z minus 1 over I times z, that's from the differential. We can cancel the i's right here. And now we have to go ahead and determine a number of properties of our integral, of our integrand actually. We need to find all the residues, all the poles, and we need to find branch points and branch cuts so that we can avoid all of those and construct a nice contour to do some contour integration. So first of all, our branch point is z equals 1 because that's the point where the argument or the input of the natural logarithm is 0. In order to find the branch cut, we know that the branch cut will always occur when um, the input of the natural logarithm is a negative number. So if alpha is a positive real number, then negative alpha is a negative real number. So we just solve for z in this equation, and we find that our branch cut runs along z equals 1 minus I alpha. We have a pole at 0, clearly, just because of this z right here. And we have a pole when this natural logarithm becomes 0 as well. But that actually happens at z equals 1 plus I, so it's outside of our circle, so we don't really need to worry about it. So this is a little graph of what our contour looks like right now. We have C1, which is this blue curve. We have a residue at 0, or a pole at 0, sorry, which has a residue. And we have this other pole over here. Now our branch cut actually runs from z equals 1 all the way down to negative I infinity. And so when we're closing this path C1, we cannot close this path C1 into a perfect circle, because then if I zoom in a ton, we would cross z equals 1, which is actually the branch point. So instead what we're going to do is we're going to make an infinitesimally small semicircle that sort of bows inward here so that we can go around that point z equals 1. And I know it looks like these paths are touching right here with this blue line and this red line, but if you go ahead and do the limits, you'll see that they really shouldn't cross it. I'm just bad at drawing this. So this path epsilon 1, together C1 and epsilon 1 are going to make a full closed contour, so we can use the residue theorem. So first of all, the integral of f of z dz over epsilon 1 is going to be 0, because first of all, the length of the integral, as we take the limit as epsilon goes to 0, is going to go to 0. And as z goes to 1, the absolute value of natural log z minus 1 over I is also going to go to infinity. And since that's in the denominator, that means our f of z is going to go to 0. So our f of z is going to 0, and the length of our integral is going to 0. So we can safely say that the integral over epsilon 1 is going to go to 0. And that means that overall our full contour, which is going to be the path of c1 plus the path of epsilon 1, is going to be I1 plus the integral over epsilon 1, which is just 0. And this is going to be 2 pi I times the sum of the residues. So it's 2 pi I times 1/4. This was just a factor that was in our integral. And 1 over natural log of I, because we're taking z equals 0. And natural log of I equals I pi over 2, and this just gives us a result of 1, or I1 equals 1. I2 is evaluated in exactly the same way, so I won't go into too much detail. The important thing right here is that now we're taking z equals e to the negative 2ix, which means that our contour runs in the opposite direction. That'll be important in a moment. So we do the same simplifications as before, and we end up with this integrand. And here's our graph right here. We have our two poles. One of them is outside, and our epsilon 2 is exactly the same path. It's just running in the opposite direction as well. Our branch cut in this case goes upwards, so we still have to avoid it. And overall, it's pretty much the same calculation here. The only difference is that now we actually have a negative sign here because the contour runs clockwise rather than counterclockwise, so that means the value of the contour integral is negative 2 pi I times the sum of the residues. And then this that's balanced out by the fact that we have a negative I pi over 2 for our... We have a negative I pi over 2 for our natural log of negative I, and this equals 1. So that means I2 equals 1, and overall our integral I is just I1 plus I2, which equals 2. Now, one thing I want to note is this was a very complicated and a little bit confusing of a solution to what looked like a problem that there was probably some clever trick that I missed. So please comment and let me know if you find a nicer solution to this problem, because I really think that there should be something easier than these crazy circular contours. Though, honestly, I do find my solution quite beautiful as well, especially when we had such a complicated integrand that just evaluates to a completely whole number. So thank you so much for watching this video. I hope you guys enjoyed. If you have integrals to suggest, please throw them down in the comments, or you can join my Discord and send them there. Thanks for watching, and I'll see you next time.